Hi ladies and gentlemen, this is Ms. Skokin. We are going to be learning about section 11-2, volumes of prisms and cylinders, as a continuation of our three-dimensional geometry unit. However, before we do that, we're going to learn about something called the apothem. The reason that we're going to learn about the apothem is it helps us use a kind of a shortcut in finding the volume of some of our three-dimensional geometric figures. Let's start by taking a look at the diagram. There's definitely a lot going on in this diagram, but let's start by seeing that we've got a pentagon. The polygon that we're going to be talking about in this case is a pentagon, but it could be any regular polygon. It just so happens that ours is a five-sided, five-angled pentagon. So we see that we have a pentagon, and we see that around it is a purple circumcircle. And you can see that each of the endpoints, or I should say the vertices of the pentagon, are intersecting with this circle. So the pentagon is circumscribed by the circle. We also see inside the pentagon another circle called an incircle. And this incircle intersects the pentagon at the midpoint of each of the different sides. So that midpoint is going to be important to us. It's going to help us to find the apothem. Usually when we talk about a radius, we're talking about a radius of a circle, but this time we're talking about the distance between, or the segment, I should say, that goes from the center of the polygon, the pentagon, to the vertex. So we have a pentagon with 5 angles, one center, but that means we have 5 radii in our pentagon. Again, that distance between the center of a regular polygon and the vertex. The apothem is something new, and it is defined as the perpendicular distance from the center of a circle to the midpoint of one of the sides. So we could draw the apothem to the midpoint of any one of the 5 sides on our pentagon, but we're really going to only draw it once, and the reason is because since it's a regular polygon, it's going to have the same lengths all the way around. So we're just going to use that one to help us find the length of the apothem. And the reason that we're going to be doing that is because the area of a regular polygon can be found using the apothem and the perimeter. And the formula for the area using the apothem and the perimeter is given here. A for area is equal to 1/2 times the length of the apothem times the perimeter around the polygon. So like most of geometry, none of it really gels until we have an example. So let's take a look at an example. And our example reads, find the area of a regular hexagon with a side length of 6 meters. We know a picture paints 1,000 words, so let's start by adding a diagram of a hexagon so we can draw in all of the appropriate measurements that we're going to need. Here's our hexagon, and we know that it measures 6 meters all the way around. That means each of these side lengths is going to be equal to 6 meters. And if we wanted, we know we're going to be using the perimeter in a few minutes, so if we wanted to find the perimeter of our hexagon, it's going to be the 6 sides that we have times 6 meters each, or 36 meters to get all the way around our hexagon. We want to be able to draw the apothem, and we know that the apothem starts at the center of our hexagon. So to help us out, let's draw the diagonals. Where the diagonals cross, we are going to find the center. Where all of these diagonals cross, we can clearly see the center of our hexagon. And the next thing that we want to do is figure out what the central angle is. And that's the angle, the central angle of each one of the triangles that make up our regular hexagon. Now we know we've got 6 central angles because we have 6 triangles that are all creating this hexagon. So 360 degrees all around divided by 6 is going to give us a central angle of 60 degrees. So each one of these central angles measures 60 degrees. Now remember, the apothem is going to be the segment drawn from the center of the, and is the perpendicular distance to the midpoint of one of the sides. So if the sides measure 6 meters and we split that in half by drawing the apothem, we basically have two triangles that have one side length of 3 meters and have a 30-degree central angle. Okay, so if we have a 30-degree central angle, then we actually ended up with a 30, 60, 90 special right triangle. And that means we have a consistent side length ratio from the shortest side, which is across from the smallest angle, to the longer leg, which is going to be the short length times square root of 3. I know I'm taxing your memory, but that means this perpendicular is going to be 3 root 3 long, and it means that the length of the radius of the hexagon is 2 times the shortest side length, or in this case, 2 times 3 meters is 6 meters. Okay, now we have our 30, 60, 90 triangle along with the length of our apothem, 3 times the square root of 3 meters. Now we're actually ready to use our formula for the area of this hexagon. Now, just a reminder, we went through a lot to set this up with our example. We're not going to have to go through as much the next time and moving forward. Once we get used to finding the apothem, we're going to be able to find it a lot more quickly. So don't panic. This isn't going to be the same lengthy process that we used this time. Okay, our formula is area of the polygon is equal to 1/2 times the length of the apothem times the perimeter of the polygon. We're going to plug in 3 times the square root of 3 meters for our apothem length, and we're going to plug in for our perimeter what we found a little while ago, the 36 meters. Remember, area is going to be a square unit, so we have meters times meters, which is going to give us square meters. This is actually going to give us 54 times the square root of 3 square meters, but we know we want to have an approximation, let's say, to 1 decimal place. And if we put this in our calculators, we're going to find it's equal to 93.5 square meters. Again, 1 dp of accuracy. Just as a reminder, our purpose in figuring out what the apothem is, of course, is to find the area of the polygon, but what we're going to be doing with the area of the polygon is plug that into a volume formula for finding the volume of our three-dimensional figures. To give you a little bit of practice, of course, there's a now you try. So you're going to be working on this on this problem. Find the area of a regular pentagon with side length 8 inches. And of course, start with a drawing, label everything, show your work, and then turn the video back on. Just as a reminder, if you do not end up having a special right triangle, you are well equipped with SOHCAHTOA to find the missing length that you need, which is that perpendicular apothem length for the formula. So don't be afraid. SOHCAHTOA is your friend. Turn the video back on when you're ready to check your answer. So finding the area of our regular pentagon with side length 8 inches is definitely a multi-step procedure to be able to use the area formula that uses the apothem. However, once we use a little bit of our prior knowledge to find the length of the apothem and the perimeter, it's actually very straightforward. So again, I've shown a lot of work here. That is for the purpose of you being able to follow all of the procedure. And if you have questions, definitely bring them up in class, but we will be using the apothem in the next couple of sections in order to have the area of the base for purpose of using in a volume formula. Anyhow, that is it for the apothem, and I'll see you back on the next video for volume of prisms and cylinders.